Like alkyl halides, alcohols can do both substitution and elimination reactions. In this highlight video, we'll discuss the elimination reactions of alcohols. After watching the video, you will be able to contrast the different approaches to carrying out elimination reactions on alcohols. Like the substitution reactions of alcohols, elimination reactions are challenged because hydroxide is such a poor leaving group. Let's compare the elimination of an alkyl halide with the elimination of an alcohol. So remember that if we treat an alkyl halide, secondary in this case, with a strong base, we can trigger either an SN or an E2 or E1 reaction. Here I'm going to show an E2 elimination. This leads to the formation of our alkene. Here we've followed Zaitsev's rule to form the most stable alkene. To try to do this for an alcohol, the alcohol is a poor leaving group, and so this reaction doesn't work. We have two different strategies to get around this problem. First, like we saw before, protonation of the alcohol gives us a water molecule that's now a good leaving group, and we'll also see the elimination of an alcohol using a different phosphorus reagent. The elimination of a tertiary alcohol can be triggered by the use of a catalytic amount of a strong acid. So here we're using sulfuric acid. Let's look at how this would take place. Just like for the substitution reactions, the first step is protonation of the alcohol. This gives us a water molecule here that's a good leaving group. Because we have a tertiary center, the water can leave, leading us to a relatively stable tertiary carbocation. Now, if we were doing a substitution reaction, the conjugate base of the acid that we used would act as a nucleophile to complete our substitution. So this is why we've used sulfuric acid here, because what we want is for the acid that we use to have a non-nucleophilic conjugate base. Alright, so the conjugate base of sulfuric acid, let's just write it out over here, is very non-basic. Notice that the minus charge is on an oxygen next to these other sulfur-oxygen pi bonds. This minus charge is delocalized between all three of those oxygens, and it makes it very non-nucleophilic, so we don't get substitution reactions instead of elimination. So instead, the conjugate base can pull off one of these beta protons. The electrons can then go to form the pi bond. So what kind of a mechanism does this look like? So this would follow an E1 mechanism, right? Because our leaving group is coming off, forming the carbocation intermediate, which then leads to our product. In general, elimination reactions of alcohol, which are called dehydrations, because we're losing water, just like if you get dehydrated yourself, you're losing water, follow a reactivity order of tertiary, like we see up there, is the fastest, faster than secondary, and faster than primary. So here's an example of a primary alcohol doing an elimination reaction. The first step is the same as we saw before. But in this case, because if the water just comes off, it would form a primary carbocation, which is very unstable. This reaction is going to follow an E2 mechanism. This is going to come here, pull off this beta proton, form the pi bond, and water comes off to form this double bond here. And so this is obviously all in one step. This is an E2 mechanism. So, tertiary and secondary alcohols will dehydrate by E1 mechanisms, and primary can dehydrate by E2. Once a carbocation forms, it will rearrange if a more stable carbocation can be generated. So let's look at this example. Notice we have this secondary alcohol on a position next to a more highly substituted position. So like before, we first protonate the alcohol. The alcohol or water can leave to form a secondary carbocation. Now, because we have such a highly substituted center adjacent to that carbocation, right, this one is secondary. In this case, we can have a methyl group shift, a 1,2 methyl shift, which leads to a more stable tertiary alcohol. Then, because we used, in this case, we used tosic acid, toluene sulfonic acid, which has a very non-nucleophilic conjugate base. Let's go back this way. It can remove a proton following Zaitsev rule. Let's go here. This can form the pi bond, and we generate the most stable alkene. Remember, the most stable alkene is the one that's most highly substituted. Now, if we step back and look at the reactions we've done up to this point, we might imagine that this carbocation could also be generated from other species as well. So what if instead of starting with an alcohol, we started with a secondary bromide? Now, if we did this reaction with a weak base, bromide could come off, it would form the same carbocation, and we would also get this same type of carbocation rearrangement. So once the carbocation is formed, it doesn't really know where it came from. It doesn't matter where it came from. Once that intermediate's formed, it can do the same types of reactions wherever it came from. So far, we've only looked at acid-catalyzed dehydration reactions, but some organic molecules are not stable to acid, so we would like to have conditions that are non-acidic. So the use of phosphorus oxychloride in pyridine is a non-acidic, actually more of a basic condition. So this might be your conditions of choice if your molecule is acid sensitive. It's similar to the others in that what we're going to do is we are going to make that alcohol into a good leaving group. So we put this phosphorus right on the oxygen. Like this. The proton on the oxygen can then be removed with pyridine because it's in a base, so this is just an acid-base step. And then pyridine, another molecule of pyridine, can remove a proton to trigger this E2 elimination. Okay, so this is E2, and the key thing is that it's non-acidic. Let's work a few examples. So let's just fill in the products. We don't have to show the whole mechanism for each of these problems. Here in the first one, we see we have a secondary alcohol. We're using this sulfuric acid, which has a non-nucleophilic base, conjugate base, and so this should be an elimination reaction. It's secondary, so it should follow an E1 mechanism, right? And so once that carbocation forms, we will generate the most stable product. So this will eliminate towards the methyl group. All right. In the second one, we're using tosic acid, which is a similar situation. We have a secondary alcohol. This should also be E1. We would form a secondary carbocation here that has a very highly substituted center next to it. So this one is going to be interesting. Let's just draw out. I'm going to do two steps here. I'm going to protonate the alcohol and have water leave. So I'm just going to show the carbocation. And notice that this center next to the carbocation has two different types of groups. It has two methyl groups and it has an ethyl group. So both the methyl, we've seen 1,2 methyl shifts. Okay, let's draw this one in. That would leave one methyl group here and one methyl group here. Oops. And this would be the carbocation where the methyl group moved from. But it's possible also for the ethyl group to shift. And in that case, we would get this. And an ethyl group would move here and a plus right there. All right, so would we get anything different in this case? So let's follow up to our products up here. All right, tosic acid, or the conjugate base, would remove a proton. It's going to remove the proton here from the more substituted side to give this product. And in this, for this intermediate, a similar thing to give us this alkene. So are those the same or are those different? These end up being the same, right? But notice that the carbocations are not the same, right? This carbocation here is next to the ethyl group, whereas this carbocation here is just between the two methyl groups. So the take home here is that when we do 1,2 or when we see 1,2 alkyl shifts, methyl groups can shift, ethyl groups can shift, other alkyl groups can also shift. All right, what about the next one? Secondary alcohol, we're using phosphorus oxychloride and pyridine. Remember, this eliminates by an E2 mechanism, and so no carbocation will be formed, and so rearrangements are not possible. And so this will just form the elimination that we would expect. Because there's no hydrogen on that center up there, it would have to eliminate to the only side that has a beta hydrogen. The last example, we're going to form the alkyl sulfonate up here as a good leaving group. We're going to use a strong base. It's going to follow a Zaitsev elimination, just like this.